Stereoscopic projection mapping allows a user to see a 3D object, floating over a physical surface of an arbitrary shape, using projected imagery. This technique has been applied for a wide range of fields, such as teleconferencing and museum guide. Stereoscopic projection mapping is achieved by projecting two images with proper disparity for each eye in a time-sequential manner. The projected images are observed through active shutter glasses consisting of liquid crystal shutters, which prevent interference between the two images for both eyes and provide binocular cues. On the other hand, current stereoscopic projection mapping is not capable of providing the correct focus cues. The resultant vergence accommodation mismatch causes significant discomfort, fatigue, and a distorted 3D perception for the observer. Our primary technical contribution is to attach electrically focused tunable lenses, ETLs, to active shutter glasses to control both vergence and accommodation. Specifically, we apply fast and periodical focal sweeps to the ETLs, which causes the virtual image of every part of the real scene to move back and forth during each sweep period. We project a target 3D object from a synchronized high-speed projector, at the exact moment that the virtual image of the projected imagery on a real surface is located at a desired distance from the ETLs. The frequency of the focal sweep is higher than the critical flicker fusion frequency, so that the observer perceives the time integral of the scene appearances during the sweep period. Consequently, our technique can provide the correct binocular and focus cues. We projected 3 Stanford bunnies on a flat screen, such that the distance of the virtual image of each bunny from the ETL was the same as one of the physical objects. Here, the focus point of the camera was changed from the far to the near of the physical object. The projected bunnies, as well as the physical objects, appeared focused from the top to the bottom according to the focus distance movement. The proposed method could provide a multifocal view in projection mapping, while presenting the physical objects without any focus modulations. We verified whether the proposed system could provide the correct focus cues when the projection screen is non-planar. The focus point of the camera was fixed at the front projection plane. The right side of the teapot appeared blurred when observed without using our technique. On the other hand, all parts of the teapot appeared focused when our technique was applied. We verified whether the proposed system could provide the correct focus cues when the projection screen moves. The bunny observed without using our technique appeared blurred at certain screen poses, while the one observed using our technique always appeared focused. We constructed a prototype system consisting of a pair of LC shutters, a pair of ETLs, and a high-speed projector. The ETL's focal sweep is synchronized with the projection timings and the opening and closing timings of the LC shutters, to achieve multifocal stereoscopic projection mapping. We conducted a user study to investigate the effect of the vergence accommodation conflict on the depth estimation accuracy of a human observer, in stereoscopic projection mapping. In each task, participants were asked to move the physical pointer by hand, until they perceived that it was located at the same depth as the projected virtual target. The results showed that the proposed technique could mitigate the vergence accommodation conflict, and significantly reduce the distortions in perceived depth in stereoscopic projection mapping.